Hi everyone, welcome to another session of the HBL files. Today we will be discussing about phase difference. The phase difference between two waves tells us how much one of the waves is leading or lagging behind as compared to the other. It's like the relative position of one wave with respect to the other. The phase difference can be expressed in terms of the fraction of an oscillation, in degrees, or in radians. Let's have some examples. In the first example, we have the displacement versus time graph of two waves, and the waves have the same frequencies and amplitudes. So to begin with, I'll be picking a point on the first graph. I'll be picking this point over here. The corresponding point on the second graph will be around here. Now, how did I know that these 2 points are corresponding points? Notice that the behavior on the first graph, for this part of the first graph, will be to have an increasing positive value for the displacement. Now, on the second graph, the closest part that has the same behavior will be this part over here. Okay, now I'll be using the first graph as my reference. This mark here shows us one complete oscillation for the first wave. This is for half of the oscillation of the first wave and 1/4 of the oscillation. Notice that the corresponding point on the second graph is located along this mark. Now let's proceed in identifying the phase difference in terms of the fraction of an oscillation. Looking at this diagram, we can immediately say that the phase difference in terms of the fraction of an oscillation will be around 1/4 of the oscillation, because the corresponding point on the second graph lies along 1/4 of the oscillation of the first graph. Now, converting this fraction of an oscillation into degrees, we just have to remember that one oscillation is equal to 360 degrees. Using this as a conversion factor, this tells us that in degrees, the phase difference is around 90 degrees. Then third one, in radians, we'll make use of this conversion factor. 180 degrees is equal to pi radians, giving us pi over 2 radians. That means, for this example, the phase difference will be 1/4 of an oscillation, or 90 degrees, or pi over 2 radians. Next. Again, we have two waves. And to begin with, the solution for the phase difference, let's identify corresponding points. For the first wave, the black one, I'll be using this point over here. And the corresponding point on the second graph, the green graph, will be around this point. Using the first graph to be our reference, this marks the one complete oscillation for the first graph and half of the oscillation of the first graph. Since the corresponding point on the second graph lies along half of the oscillation of the first graph, then the phase difference will be 1/2 of an oscillation. Converting this into degrees, we have 180 degrees. And finally, for radians, it will be pi radians. So the phase difference for this item will be half of an oscillation, 180 degrees, or pi radians. Next. Now, in this example, this is quite different as compared to the first two. Why? Notice that the two waves have different frequencies. Now, let's pick some corresponding points on the waves. First one will be this. Notice that if I pick this point on the first graph, the corresponding point on the second graph will also be at the same position. So there's no phase difference between the two waves if you look at this position. But if you consider, say, for example, after one complete oscillation of the first graph at this point, the corresponding point on the second graph will be here. Notice that there was a change now in terms of the phase difference. For this point, there was no phase difference. But on or after one complete oscillation of the first graph, they now have a phase difference. So when you have waves with different frequencies, it does not make sense to identify the phase difference, because as you go along the waves after certain time intervals, the phase difference will continue to change. So again, we usually don't identify phase differences for waves that have different frequencies. Okay, let's have some further examples. So the same instruction, we just have to find the phase difference in terms of the following: fraction of an oscillation, degrees, and radians. Okay. So in this item, we now have two waves again. Same frequency, but now different amplitude. Again, as long as the waves have the same frequencies, even if their amplitudes are different, we can still find a phase difference. So I'll be picking corresponding points. For the first wave, this wave over here, I'll be picking this point. So on the second wave, that the corresponding point will be around here. Using the first wave as a reference, this marks one complete wave and half of the wave or wavelength. So the fraction of an oscillation, or the phase difference in terms of the fraction of an oscillation, will be 1/2 of an oscillation, since the corresponding point on the second wave is found at the half of the oscillation of the first wave. In degrees, this is around 180. And in radians, this is, of course, pi. Okay. Last one. Same procedure, guys. I'll be picking this point, and the corresponding point on the second graph will be around here. Using the first graph as a reference, this marks one complete oscillation, and this is half of the oscillation. Notice that one complete oscillation is around 8 squares, and the corresponding point on the second wave is found on the third square from this point over here. So the fraction of an oscillation, or the phase difference in terms of the fraction of an oscillation, will be 3/8 of an oscillation. Again, why? Because one oscillation is divided into 8 squares, and the corresponding point on the second graph was found at the third square. Okay. Converting this into degrees, we have around 135 degrees, and in radians, this will be 3 pi over 4 radians. So that's it. That's how we find the phase difference between two waves. I hope everything's clear, guys, and thank you for learning with me today. See you in the next session of the HBL files.